What is a limit? A limit is defined as the value that f of x approaches as the x value approaches some number. If we name some x value c, where f of x is undefined at c, the limit of f of x on our graph at x equals c will be f of c because all of the values of f of x get closer to f of c as x gets closer to c. We can call this f of c the limit, or capital letter L. We can write that definition out like this. The limit of f of x as x goes to c is equal to L. Using this definition of our limit, we can switch it around and say that if you give some number f of x as close as you want to L, then you can also find a number x sufficiently close to c. What this means is, if you take our function and say that this limit as f of x approaches c is true, then you can give some f of x in a certain range of L that will give you an x value in a certain range of c. If this rule works for all ranges as x goes to c, then you can truly say that this limit does exist. Intro to Delta-Epsilon. In order to make this definition more coherent, we can say that this range around L of f of x is a number epsilon, where the range is positive and negative epsilon from L, and the resulting range around C is a number delta, where the range is positive and negative delta away from C. If you can find a range delta that matches with the range epsilon, and the distance between x and c in the range delta corresponds to a distance between f of x and L inside the range epsilon for all x values, then the limit definitely exists. The delta-epsilon definition. The delta-epsilon definition looks formally like this. The absolute value of x minus c and the absolute value of f of x minus L is just a fancy way of showing the distance between x and c, or f of x and L. Proving a limit using the delta-epsilon definition. Let's make our f of x be a piecewise where f of x equals 2x at every location except for our c value of 5, and place a jump discontinuity there. As you can see on the graph, as x approaches 5 from either direction, f of x clearly approaches 10, so we can say that here our L is equal to 10. In order to prove that this is indeed the case, we must use the epsilon delta definition. Taking the formal definition that we established earlier, we can replace the variables with the values that we defined. In order for the limit to exist at this point c, we need to find some way to make the delta part look like the epsilon part. We can do this by multiplying both sides of the delta inequality by 2, so now we have the absolute value of 2x minus 10 is less than 2 delta. Because we established that f of x was equal to 2, then those two values are interchangeable, thus making the two absolute value portions of the inequalities identical. Therefore, we can conclude that 2 delta equals epsilon, or delta equals epsilon over 2. Because f of x equals 2x at every location, We know that delta equals epsilon over 2 at every location on the graph, so the limit as x approaches 5 is definitely 10. Disproving a limit using the Delta-Epsilon definition. We can also use the Delta-Epsilon definition to disprove a limit. Let's take a function where the limit doesn't exist at c, say a piecewise, where f of x equals 2x when x is less than c, and f of x equals 3x when x is greater than or equal to c, where c equals 5. Say we assume, mistakenly, that the limit of this function, or L, is again equal to 10. In order to prove or disprove this one, we will have to work on each part of the piecewise separately. If we start with the part where x is less than 5, then f of x equals 2x, and we can write our definition out. The absolute value of x minus 5 is less than delta, which goes to the absolute value of f of x minus 10 is less than epsilon. Again, we try to make the two parts look alike. So again, we multiply both sides of the delta inequality by 2. We get a similar result to the proof we did earlier, where delta equals epsilon over 2. Now, we look at the other part of the piecewise, where x is greater than or equal to 5. Now, f of x is equal to 3x, so to match our two sides, instead of multiplying by 2, we multiply by 3. And we get the absolute value of 3x minus 15 is less than delta, which goes to the absolute value of f of x minus 10 is less than epsilon. We can see here that although the f of x lines up with the 3x, the 15 and 10 do not match. Therefore, the definition is not fulfilled, and the limit of f of x as x goes to c does not exist. In conclusion, the delta-epsilon definition can be used to prove or disprove a limit of a graph at a certain point.